I'm Adi Natan from SLAC. I'll try to, since this is the last talk before lunch, I know it's a sensitive matter, so I'll try to treat you like Henry VIII treated his wives. I won't keep you long. So these... I'm
now worried about my neck.
Sorry. Yeah. So the theme of this workshop was understanding quantum coherence of systems of various complexities, and in particular the role that physics has in order to promote this subject. And a common trait or a common feature of these complex quantum systems is that electronic surfaces cross each other. So we have lots of places where crossings appear. In graphene, for example, I'm sure you discussed earlier today and in days before, you have the Dirac points of contact between the bands where the linear energy dispersion curves crosses. But graphene is very cool. But in almost any polyatomic molecule of 3 atoms and more, you have these potential energy surfaces that cross each other, and these are conical intersections. Now, conical intersections has tremendous importance in chemistry and also biochemistry, I think. These are energy funnels or efficient and ultra-fast routes to transfer energy from one place to another in a non-radiative manner. And this is important in certain chemical reactions and in photo processes like DNA protection from UV and so on. So if one wishes to understand how quantum coherence evolve in these complex systems, it must also include the interaction around conical intersections. This is part of the deal. Now, as in physics, we try usually to reduce the complexity and keep the essence. And this brings me to talk about the existence of the so-called light-induced conical intersections in the simplest molecule in nature, which is H2+. So it's a bit paradoxical, but bear with me and we'll see how it goes. And we start with the basic of the basics. We start with the Born-Oppenheimer approximation, and we'll see how conical intersections are produced. We'll then talk about the case of diatomic molecules, and if you think of it really shortly, you'll see that it's impossible to have conical intersections in diatomics. And then I'll discuss some experimental results and simulations that we have. And we start with the Born-Oppenheimer approximation. So thank God in nature, we know that we can have these type of separation between different time scales. Electrons are so much faster than the nuclei, so we have what we call a adiabatic separation. And the easiest way to see that is in this 2-channel toy model, 2x2 matrix, very simple. We start with an Hamiltonian that has some free terms that in this case are just, they're just linear functions, right? Just 2 lines that cross each other. And we have some coupling between them. And in order to see what happens, we just diagonalize the system and we'll get these so-called adiabatic energies. And we immediately see that they can't cross, right? Because in order for them to cross, we need this square root term to be 0. But it can't be 0. We have only positive terms here. And this is seen here in this picture that I'm just plotting. And so if we start with some wave function, let's call it psi1, we will travel across this avoided crossing. And this was discussed many, many times. And okay, that's good. That's how nature works. Another thing to mention is that the adiabatic the adiabatic wave function character changes in the avoided crossing. We start with something, we end up with something else. And so you can see it's phi1 goes to phi2. Now, there are cases when we'll have diabatic types of crossings, when stuff goes really, really fast. Often in nature, we don't see that because electrons will be always faster. In that case, the adiabatic approximation fails, and in that sense, it's not only that things go slower or faster, it's the overall energy that is not kept minimal. Here we reduce the energy change. Here we'll lose a lot more energy, but we keep the structure of the wave function, the profile of the wave function. So this is right, Wigner and von Neumann and Born and Oppenheimer, 1930 something. Let's ask, when can these curves cross? So there is the boring case where they have different symmetries, so obviously they don't talk to each other. But another case is when the adiabatic parameter, which is r in this case, this coordinate is not a scalar, rather a vector of some dimensionality. And we can see this here. Again, we need to vanish this square root, and we have basically two conditions. So the first condition is that delta, or that difference between the potential curves needs to be 0. And this means that we'll find some R naught that will satisfy that. But this R naught cannot be the same one for D. But if R is not a scalar, if it's a vector, then I can find Rx and Ry such that together I'll have this type of crossing. And the reason I selected, of course, this linear type of expressions is everything is linear if you really look at the neighborhood of the crossing. You can always, almost always, approximate it to be a linear function, and this brings the birth of conical intersections, basically. Now, in order for that to happen, we need R, which is a vector, and this happens at least for a triatomic molecule, because only then we have enough degrees of freedom for that condition to be fulfilled. Okay, very simple. Everything is known, textbook material. And that's how it looks. So, again, a quick recap. These conical intersections are very common, very ubiquitous. We have, they're very important in the fact that they do this non-radiative energy transfer and are important. But as an experimentalist, what challenges me is the fact that they're set. I can't do anything with them. They're inherent features of the molecule I'm studying. So it's in some internuclear separation, in some coordinate, at some point. That's what we have in some energy. So it's really hard to access or to measure them. That's been challenging. Another thing that needs to be mentioned is the fact that these are topological interesting creatures allows or brings the existence of a geometric phase into play. Now, we can go and discuss this in detail, but I'm sure people understand what I'm saying when I'm just mentioning the geometric phase. And you can imagine cases when you encircle that hole or that singularity, and then you must acquire a pi. And this is just to get the wave function single valued. So Berry got that in 84, and I don't know how much is it important in nature, but obviously it's part of a property of such a phenomena. So let's talk about diatomic molecules. In diatomic molecules, in free diatomic molecules, this is impossible. But now, what about diatomic molecules in strong laser fields? No, they're no longer free in that sense. So I still use the same two-channel 2x2 matrix, and I now use the Floquet approximation. So we dress one level with a photon versus the other. We still have this dipole coupling. And now I define this dipole coupling to be some function of the internuclear separation. This can be a constant for this matter. It doesn't really matter. Times some energy that the field has, which is not really, if it's really Floquet, then it's a CW. So I'm just trying to illustrate what I mean here. And there's some angle between the polarization of the field and the molecular axis. And here already, we have 2 degrees of freedom. So the adiabatic parameter R the internuclear separation is not alone. We have theta, an angle between the laser polarization and the molecule. And so you can imagine that now I have a condition where I can find some r that will satisfy this condition, and I can find some theta that will satisfy that condition, such that the entire square root, if you remember, of that adiabatic energies will vanish. And this was pioneered by Mosev and Cederbaum. This is one of the references. And it sounds like, okay, but haven't people seen that before? This is, we did these experiments, people did experiments a long time ago, and still, what are the implications? How can we really say that we see something important in that aspect? And so we decided to treat it in the really simplest molecule available. This is just H2+. So H2+, you have a bound potential and an unbound potential, just these two levels. That's enough to describe our system for the intensities I'm going to use. So it's the 1s sigma g here and the 2p sigma u. We have vibration levels until we don't. And once we induce a strong laser field, in that case, a laser field that dresses this potential curve by 1.55 eV, which is almost 800 nanometer, not surprising there. We see that we'll have a crossing when theta is 90 degrees, and the biggest avoided crossing would be at 0 degrees. And for sake of the next slides, I will just mention that this vibration level that we have here, the 9th vibration level, is closest to resonance. This will be important for next slides. So this picture is one thing. We can also see it, this entire phase space of angle and internuclear separation in the following graph. So you can see that this is internuclear separation. These are angles, 0 to pi, to 2 pi, and this is the point. This is that crossing. I prefer this view. So you can see the top and bottom energy curves. So the conical intersection in the bottom adiabatic curve is a local maxima, whereas in the top one, it's a local minima. And now we say, okay, if we propagate a wave function on top of that, will it matter? Will we see something that we haven't seen before?
I'm kind of confused here.
Yes.
This angle theta.
Yes.
This angle between polarization and double molecule.
Yes.
So in a sense, all the picture which you draw, it's like for different molecules because...
Very good question. So what, in reality, what we'll actually measure, let me answer in two parts. The first part is, in reality, we measure a non-coherent ensemble of molecules, right, each of them in some J state. And this brings me to the second part of the answer. It's not really the angle that matters. It's the J state, right? So if I'm in J0, I see all angles. And the reason I choose, I really prefer to look on this phase space of angle versus internuclear separation is because at the end of the day, that's what I measure. So when I calculate, I'll calculate the angular momenta and so on. But this is eventually the thing that I measure in my detector. I measure angles. That's the reason. So I'm sorry for confusion. So, okay. So we solved it. We tried to simulate this. So this is a time-dependent Schrödinger equation simulation that represents a molecule in the 9th vibration level as an eigenstate. This is how we start. J0, super cold. We don't have this in reality, but it's easy to understand and solve. And this is how it looks. Now, the color map is a bit misleading. It's not uniform, so it's slightly logarithmic in order to show you the important aspects. And this is before anything happened. In that phase space, you see this small x as the position of the conical intersection that will induce when the laser will be on. And here we have an absorbing boundary that allows us to bookkeep whatever population dissociated. So we'll plot here the dissociating probability as function of time. And we'll just sum this. This is what happens when we consider the pulse of 30 femtoseconds of intensity of 10 to the 13 watts per square centimeter. This is what we did in the experiment. So this is 20 femtoseconds before the peak of the pulse. So already we see things that we can easily understand. One of them is that this population is dissociated, and the closer the molecule is to in access to the polarization of the laser, the more efficient the dissociation is. And if you really cross the line here, you'll get the typical cosine square type angular distribution. But already we see that there is some accumulated part of this wave function that cannot cross the conical intersection. Remember, it's a local maxima in that bottom potential curve. Now, other things, of course, happen, but let's move to the actual peak of the pulse. And here already we see very interesting things. So, again, a wave function that was parallel to the laser polarization dissociates. But already we see here that we start to have interferences. And these interferences can be seen as a scattering or point source scattering between something here, which is the conical intersection that we induced, and the part of the wave function that was outgoing. So it's like, it's not really scattering in the sense that we consider, but in that phase space, we mix our very low J states with very high J states, such that the overall internuclear separation and J state description interfere. And this is this curvature here, and you can see these lines here. And the fact that you have this horseshoe shape is also because of the part of the wave function that circumvents that conical intersection, because remember, it's a local maxima. Of course, this is what I'm showing here is the probability density, the overall probability density. Now, already we start to see that these interferences will affect in the sense of the angular distribution. We can start develop type of nodes in that sense. If we go further, this is more noticeably seen. So you can see that we have here interference in the angular distribution, and these nodes are more clear. And if you go really to much after the pulse ends, or probably mostly after the pulse ends, these nodes are really noticeable. And this, in a sense, was not seen before. So this was predicted by Moseev and Siderbaum, and this is a feature or trait where such a angular distribution behavior would be because of that light-induced conical intersection. Otherwise, you'll get cosine square, or cosine to some power. This is, some Legendre polynomial. This is what we used to when we just look on angular distributions of photodissociation. And I just plotted the rest of the simulation. So this was for the 9th vibration level, which is closest to resonance, which has a very high overlap between the major part of it and the conical intersection. Let's look.
This is wave packet solution of Schrödinger equation.
Yeah. So this is just time propagating both in angular momentum and in internuclear separation of the Schrödinger equation, where we started with an eigenstate. We haven't started with a wave packet. Very simple. This is how it looks for different vibration levels when we started as eigenstates. So this is what I just plotted to you, only I reversed it in 90 degrees for reasons you'll see in the next few slides. This is how the 8th level is seen, and this is how the 7th. So you can see already that these nodes change. We count less nodes here. So if here we have these 3 nodes, here we'll have only these 2, here we have only this 1. And why is that? So there are several reasons. One reason is the actual overlap between these eigenstates and the conical intersection. V equal 8 is less resonant. So it takes time, only in the closer to the peak of the pulse, you start to populate higher J states that together will have overlap with the conical intersection. Remember, you can transfer population in J not necessarily via the conical intersection, also just by non-resonant Raman. So everything happens at once. So we have these two-path type of processes that happen. One of the paths is just non-resonant Raman. we don't need anything for that. The bandwidth of the laser, 30 femtoseconds, is strong enough to, is broad enough to induce that. So
What was your frequency?
795 nanometers.
So it's sort of like from the ground state to the dissociation level?
So yeah, so from the, excuse me for going back. So yeah, so this is 795 nanometers, and there's some bandwidth there. Now the bandwidth is about 40 nanometers, fully half max, but there are tails, right? Now I'm not yet mentioning the actual experiment. This is just a simulation. Okay, let's wait for that. But these are vibration levels for J0. If we have higher J's, of course, there will be overlap of lower vibration levels with there. And you can populate these higher J's without taking into consideration the crossing. This is what I just mentioned. So this is how we understand why we have less nodes. We just have less time to interact with the conical intersection and to develop these interferences. Another reason is the actual nodal structure of the wave function itself that we start with. So the ninth level has several nodes in that phase space. Seventh has less nodes. So when they curl around the conical intersection and then interfere with the reflecting parts, we'll have less of them to begin with. So it's kind of a convoluted approach where both time and the actual initial state play. Okay, what are we actually measuring? We're measuring angular distributions. We don't have this cool way to see what happens in angle as function of femtosecond time, or at least I don't at the moment. So this is the experiment. You can see already that I'm Israeli because my ion beam flies from right to left. Whereas in many talks I see that it's the other way around. So we start with an ion beam. I'm not going into really too many details how we produce this in a Nielsen ion source and so on and so forth. Just saying it's an H2 plus ion beam, 4 kilo electron volts, well schemed into a spectrometer where we dissociate the molecules with a strong laser field. And we can measure in coincidence both the charge and the neutral fragments on an MCP. And we detect both the time of flight and the angular distribution. Such that together in coincidence, we can trace back the entire momentum information of each dissociation event. Now, it's important to know that this ion beam is not coherent. We ionize H2 with a filament many microseconds before everything happens. And this ionization is, there's some Frank-Condon overlap that already determines how our H2 plus species will be distributed, but they're not coherent with one another. So in that sense, I can treat each coincidence event as just a sample of a non-coherent H2 plus sample that of different eigenstates that we started with. What I don't know or don't know accurately is how hot rotationally was my sample, because I'm starting with a filament, heating it a lot, creating these H2 pluses, so it's not zero temperature. Far from that, probably. So this is something we need to further understand how it exactly makes a difference, and this is something we're probably try also to circumvent by starting with a colder sample. So this is a typical raw data, everything together, no coincidence, you don't see really anything. This is the time of flight. And so we can really pick a very narrow energy range and look on the angular distributions there. This is how it looks. These are our results, basically. So you can see the 9th vibration level at this energy, the 8th and the 7th. These are angular distributions as function of dissociation yield, let's call it. And this is what I just presented to you before. And yes, we see these modulations on the angular distributions. If I increase the bin size in energy or reduce the bin size in angle, if you want, these will very soon become your typical cosine square, cosine to some power. You need to really fine-tune and go to finer bins as much as your resolution allows you in order to get these features out. I think this is one of the reasons where Itzik in Kansas that measured similar things, didn't see it before. And there are other groups that are capable of doing these measurements. So let's look more carefully. The ninth, we have these several nodes here. Of course, I need to really integrate over everything here. It's a bit messy. You can see that there are some parts of these nodes that smear one another and overlap one on top of the other. Eighth is slightly cleaner, and we have these two nodes, and you can see these two nodes here. And seventh is much more simple because it only very high J states in 7 play a role here, and we have maybe a node here, and this is maybe the skink here. Now, again, this simulation was for cold molecules. This is far from the case. Another thing that makes the comparison slightly different is this Frank-Condon distribution of states I'm starting with. So I need to adjust this into the right weights, and we can do that too. Another thing that is part of the experiment is I'm starting with a finite sample in that sense. Because V equal 9 is almost on resonance, it's very easy to deplete all the V equal 9 molecules that were more or less in alignment to begin with. So there is this saturation of the probability amplitude that will create this flattening here, whereas this won't happen here. This is a much higher peak. So we need to adjust for that too. But all in all, we see things, or we see these interferences because of the existence of the light-induced conical intersection that weren't seen before. A question we ask ourselves, and we still don't have a good feel, and I of course appreciate the discussion here, is how does the geometric phase matter in such a measurement? In order to really have a geometric phase, you need to encircle this singularity. We don't do that because we start from a point that is localized slightly left to that in that picture. We don't really engulf it. This is one thing. Another thing is that it's not enough. You need to have a population both in the ground and the excited state in order to make that relevant. And so we say, okay, that's the regular Berry's phase, a type of explanation, but can we still see geometrical phase effects without that? Now, one of the things I'm not showing you here is that this is the probability density. It's not the amplitude. If you look on the amplitude, you'll see that there is a pi phase between this and this, the upper part and the lower part. And this is very understandable. I'm going from S to P. So of course I'll have this, this pi phase difference between the two parts of the plane. The question is it relevant for the geometric phase, or is it just part of the experiment? Or maybe it's both. So with that, I will stop and happy to try and think with you together in the discussion stage. These are the potential uses that we think we have now. Up until now, conical intersections are, some inherent part of any molecule which is big, hard to access. Here we produce it with a laser. So you understand, we can control its frequency. This is the position, if you want, of the nuclear separation. We can change the polarization. This is the position in the other degree of freedom. So we can really do whatever. We're not limited to just one. We can have multiple beams, or pulse shaping in that sense can help. We can also control the timing of their appearance because it's when the pulse is onsets and out goes. So it's really a very rich environment to test different control ideas. And what we hope is the understanding of how coherence and excitation evolves around these points will help understanding how this is also relevant in larger molecules, especially the combination of these type of light-induced conical intersections in larger molecules. With that, I want to acknowledge student I'm working with, Matt, which is excellent student and did part of the simulations that you saw, and Phil, my mentor. I also want to acknowledge a collaboration on the original experimental system from these guys, Vaibhav at Tata Institute, and Uri, and Yaron Silberberg and Daniel Zeifman at Weizmann. And with that, I end. Thank you.
Yes.
You start with an eigenstate, but the moment you start propagating, then so you have a wave packet.
Correct.
And so this wave packet is coupled to the excited potential.
Yes.
So do you see interference between wave packet alternatively propagating on the downward excited?
Yes. So it's a very good question. The part of the wave packet that is on the excited state, since this excited state is unbound, most of the interaction there, if it's outside of the conical intersection, is a bit boring. And the reason is that you can couple to so many J states, it's practically a continuum, and a continuum of vibrational states, so it just washes away. But the fact that the conical intersection allows part of that population to couple back to the bound states, this bound state has now many vibrations, and each vibration has many J states, many rotations. And I think this is the part where most of the contribution of all these very good-looking interferences come about.
Yes, that's what I suspect, that it is this interference between wave packet propagating in this alternative potential.
Yes, yes.
That is what gives rise to these significant patterns.
I'm a little surprised about this. You have relatively long pulses, right? 35 femtoseconds.
30, yeah.
So you're feeding into this excited state over a time that is longer than the vibration period. So
Not a lot longer, though.
Yeah, 20 femtoseconds,
Yes.
right? And you're feeding over 10 femtoseconds for 1 hour.
Yeah.
For one stretch. You're feeding over 30. So I wouldn't really think that makes a wave packet. It makes a kind of a smeared out distribution over the classically allowed part of the lowest potential current. And then I have to have comments with regard to the rotational motion. We looked into that a couple of years ago and said the temperature at minus 100 degrees centigrade, I think, that can be done in the lab. H2 is rotationally cold, so you only have like J for 0, 2, and 4, I think, and they did a convergence test and saw that I think the 3 lowest J do the job. And observe for kinetic energy releases, that's what is measured in many places, that the kinetic energy release spectra with or without rotational motion do not differ by a lot. You see small differences, but overall the rotational motion found doesn't matter.
Yes, this is also what so let me answer to both of your comments. The first comment, you're right. It's not really non-adiabatic in the sense that we're still slightly slower than your typical vibration period. However, it's just Landau-Zinner type of argument. You will still have non-adiabatic transfer. So you'll still have this mixing between some vibrational and some rotational state to some other vibrational rotation state. And this is enough to see what we see. It's not a wave packet per se.
Why not? It's wave packet.
It's a wave packet, but it's not.
It's a raw vibrational wave packet.
Yeah, it's a.
Sure, but the point is the coupling is not very strong. We thought about this as basically a vibrational wave packet that somehow gets a rotational substructure.
Yeah, but you
Kinetic
should
energy
consider.
releases that you see mimic the vibrational structure with a very hardly discernible rotational substructure on top of it.
I'll return to that. Another point is that our hydrogen is really hot. I would estimate it something like 800 degrees centigrade, maybe 1,000. I don't know. And it's another thing to consider. And we're not there yet in simulating this, but we will, I guess. Or we'll just try to, I think it's easier to just create a colder sample. Because H2 is relatively easy to have. Yes. Yeah. Oh, sorry.
So about the periphrase. No, first of all, I still kind of worry about your interference pattern because that's not exactly what is happening. The picture which you, as far as I understood, so you calculated for particular orientation of polarization, right?
Yes.
You run the program, you get wave packet, you get wave function, and then you take changes angle theta, and then you run again, get wave function, and then you make it this simulation.
No. I'm starting with J0.
It cannot be like this.
I'm starting with a molecule at J0. So it's a completely spherically symmetric. There is no angle to the molecule, right? Molecule is completely spread in angle. And at V9, at some internuclear separation or some eigenstate in that sense, and then I propagate. The propagation includes some polarization of the laser. It doesn't matter what polarization the laser is. Whatever angle you want it will be 90 degrees in some reference frame. No. What do you mean some? In the simulation, there is no angle. You start with no angle.
You are doing ensemble.
In an experiment, it's completely isotropic. I don't have any preferred angle. It's not that I'm, unlike other experiments, when I ionize with the laser from H2, then I have some cosine square distribution or something. Nothing here. It's completely
and in terms
isotropic.
of very phase, a small comment. Probably it's better to switch to another molecule where you don't have up
Unbound.
state.
Which is unbound. Yeah.
Because you are losing everything. You cannot go back.
Yeah. So I can't interfere that in that way. But that's much easier. Or simpler.
Yeah.
Other molecules.
You can take sodium too.
You try to work with sodium too in SLAC.
I can do simulation.
It's hard to. It's not easy. We tried with iodine, and
iodine it's also.
it's slow, really slow, but it's such a mess. You have so many states that couple to other states. This is the simplest, you know. This is only two states. It's, if you hope to see something, you'll see it here. Yes.
If I had a question, maybe a comment or a question. For many systems, triatomic, polyatomic, and maybe they're too messy for you right now, you already exist conical intersections that control reaction dynamics with pieces that you are getting dissociation or reformation of these things. And so it seems to me using a similar technique, you could manipulate those existing conical intersections, maybe close them, and coherently control reaction dynamics very easily where conical intersections exist just by shifting them maybe a little higher in energy or a little out of the reaction coordinate or off the reaction coordinate. So it's just goes in that. Could you comment? Maybe?
Yes. So this is one of the I guess the other one. Oh, whatever. Yeah. So this is what I meant here. Now, there was an experiment that our group did like a year and a half ago that tried to do that in CHD, in cyclohexadiene. But my understanding is that the effect of light-induced conical intersections in the way it affects any wave packet that you create is not trivial. It's just smoothing it because you still have it. And the additional degree of freedom that the laser has on the system, because it's well-defined in time and in space, in that phase space of angle and internuclear separation, makes the dynamics slightly more complicated because it's not just moving things. So you can dress potential curves and affect that in AC Stark shifting type of experiments like Albert Stolo did a few years ago and so on. But it really holds potential to, for instance, understand how coherence evolved around that in the sense that I can start and shut off this type of light-induced conical intersection next to a regular conical intersection and see how I get different spectra, for instance, from that. Uwe.
Go ahead.
Yeah, okay, my question is quick. So what would be your physical interpretation or significance of these nodes which are along the theta axis, right?
Oops.
To kind of create a spectrum of the theta.
You talk about these. These.
Well, actually, there was much better that way, I think.
Like this.
Like you have three pictures. And you
Oh,
have
yeah, yeah.
the
I see, I see.
Right, right. So if the one, two, now, what is the significance?
Okay,
It's
so,
a node that ends up, right?
yes. So, let's say, I didn't tell you maybe, but T0 here is the peak of the pulse. Okay? So, of the laser pulse that we simulated. So, you can start seeing things here develop already slightly before that peak. This node here that will then evolve to creating this bigger node. And I said that before, I'll say it again, so I guess it's not clear. So I'll move back to this picture. So we start with these nodes, right? So we have these nodes here. This is the wave, the eigenfunction that we start with. So this is one thing that we start with. Another thing is what it does because of the conical intersection. So you can see already this will create some part of the first node. But that's not enough because this won't curl enough to get that. So part of the deal is the fact that we have already a large distribution that was here that just circumvented the conical intersection. But the fact that part of this also reflected back, I don't show you a movie because it's way too messy. Too many things happen. But the fact that part of this reflected back interferes in that function in different angle in that phase space, such that when you continue in time, this will create further separation into these nodes. So actually, you have like a internuclear angular phase space interferences. You can see there are interferences here also, and interferences here. And this is because of the combined effect that I described. I don't have any better way to think of this at the moment because it looks like both play a role, both the scattering versus the outgoing contributions, and the fact that I'm starting with this nodal structure. If I'm starting with just a wave packet, this is another thing I'm not showing you. So say instead of this eigenstate, I'm starting with a wave packet. I'm ionizing from hydrogen, this is localized here, and I let it propagate. You'll still have this, because it will still curl around the conical intersection, it will be only a single, let's say it's a Gaussian wave packet, but part of it will reflect into all angles and reflect back. So if you remember, the potential phase space here is such that anything reflects here in this angle. Why does it reflect? Because it's like, if you want, a plane wave and a point source. So it's like a combination of plane waves and spherical waves in that phase space. It's not really scattering. So we'll have these diagonals, and they'll come here, and then they'll be easier to dissociate out because of the new angle that they'll acquire. So this combined thing. But in wave packet simulations that we do, not starting with an eigenset, you can also see that. It will just be a different type of modulation.
Yeah. Can you make it quicker?
You would see all of this better if you took a shorter wave packet, 5 or 6 femtoseconds, because it looks messy in your terms because
Yes.
the wave you're feeding into this wave packet, while the leading edge of it is already reflected onto itself.
You're correct.
And that makes all these wiggles in the vibrational and in the rotational.
You're correct.
Also, if you use Quantum rates, I think you tend to overestimate the vibrational temperature. If you compare with molecular ADK rates, for instance, and go through the same calculation, using molecular ADK rates, you make vibrationally colder wave packets by quite a bit.
Okay.
And then
This is the best we could guess. This is what.
Yeah, but I think molecular ADK rates are still an approximation, of course.
Sure.
But they're more realistic than quantum rates. And with regard to the averaging, it came up, there are really two averages, right? Because you make a rotational wave packet, so you have the coherence of rotational wave packets, you add them coherently. but you have an initial distribution in your molecular ensemble over which you have a incoherent. So what, you just started with the J equals 0?
Yes, yes. This is very easy, right? Of course, you need to average also the different ISO intensity shells of the laser, and the actual ionization where we produce the ions is not exactly clear. It's not really Farn-Condon, and it's also not exactly ADK. It's something, but approximately, we still get a good qualitative agreement in the features that we measure. And that's encouraging. So we can only improve the experiment now. I didn't mention, this is hot from the oven. Still not published, so I'm just sharing it. I think this is the first public share of these findings.
That's where your comment about heavy weights come in mind, right?
Come again?
You commented on heavy weights, so now we hear all this unpublished information, so should we be careful with...
Shall we write disclosure again?
Good luck. Good luck doing this.
All right, well,